So I'd like to show you an example of what's known as a reversible reaction and introduce the concept of equilibrium. And I'll start by showing you the experimental setup. On your left is a beaker that contains water that's just about at the boiling temperature, about 100 degrees Celsius. And on your right is another beaker that contains ice water at 0 degrees Celsius. And my reaction vessel, where all the action's going to occur, is this sealed glass tube. And this glass tube was made by evacuating all the air out of it and then just pumping it full of NO2 gas. And NO2 gas is a really toxic brown gas. This is the same gas that makes photochemical smog on hot days, makes the air look kind of brown. And so when we start out, I can think about, well, this tube contains some NO2 brown gas, and somehow I'm going to let the reaction start. And what NO2 can do is two of them can come together and transform into N2O4, which is a colorless gas that we can't see. So if I looked in here, I can for sure see that there's some NO2 in here, but I really don't know if there's any N2O4, and maybe this reaction is taking forever to turn into products. But up to this point in our chemistry careers, we've just done stoichiometry that says if you take some NO2, I can predict that when I let this reaction start, I should produce N2O4, reactants convert into products, and I can even predict that I should form half as many molecules of N2O4 as the number of NO2s I started out with. But I want us to watch what happens. First of all, as we sit here at this high temperature, I notice that the color is not changing if I just sit here for a while. And that tells me that apparently it doesn't look like any of the reactants are converting into products. If they were, it would be getting lighter. But I can make it look like that reaction is going to occur if I put it into cold water. And you can see almost immediately that the intensity of the brown color goes away. But it doesn't go away completely. In fact, if I let it sit here long enough, it's going to reach a state where the color is no longer going to change. It's going to seem to settle down in what we call an equilibrium position. And so clearly we have to think about carefully what just happened. Some of the brown, NO2, got converted into N2O4. That's the only place that it can go. There's no other reaction that will occur with a tube filled with NO2. And so I can tell that that happened because my color went down. So now when I look inside this tube, I analyze it, I can say, well, if I compare this to a similar tube at high temperature, which I'll pop right in there, clearly the tube on your left is darker and contains more NO2 than does the tube that's over here on your right, because it's darker. So this one has apparently more N2O4 and less NO2. But if I just swap these out, I can change those proportions. Apparently this reaction says at high temperature it likes to have more NO2 and less N2O4, and at low temperatures this reaction has more N2O4 and less NO2. And the idea that I can go back and forth and change the relative proportions is what is called a reversible reaction. I can push this reaction one way or the other. And it also tells us that inside the tube at any temperature, both the forward and reverse reactions are probably happening at the same time. Some NO2 is being converted to N2O4, and some N2O4 is being converted back into NO2. So let's just watch me push that back and forth by changing the temperature. So each one of these tubes contains what's called an equilibrium mixture. So equilibrium in this sense does not mean equal quantities of reactants and products. Clearly, if these are both at equilibrium, they can't contain the same amount of reactants and products in this tube as there are in this tube. They're not the same color. What equilibrium means is that the rate of the forward direction, the rate at which NO2 is being converted into N2O4, is the same as the rate at which that N2O4, which I can't see, is being produced, converted into brown NO2. I know that that rate, those two rates must be the same because the color no longer changes. Same thing over here. It's much easier to think about this one and say that both reactants and products are present because I can compare it to this one. But they're both at equilibrium. The rates are the same, but the proportions of the reactants and products are different. And it's those different proportions that exist at different temperatures or under different types of conditions that we call a position of equilibrium. The rates in the forward and the reverse directions are the same, but the concentrations or amounts of reactants and products that exist and never change are going to be different at different temperatures. So that's what we mean by a reversible reaction. We can push a reaction forward and backwards. The reaction hasn't stopped, it's still reacting, but the rates are the same. So to the outside world, it does not appear like there's any reaction occurring.